So I just decided I wanted to make a video about inductors at t equals 0, 0 minus, and 0 plus. But it seemed like such a big effort to stand up and go into the other room and get my computer, or to get on the computer. So instead, I downloaded screen recording software for my tablet that I happen to just have within arm's reach, and installed that, and we'll see if that works. Okay, so this is also very important. There's another video about capacitors at time t equals 0. So being able to get the right answer to RC and RL circuits, you really have to know what happens at time t equals 0. And one thing that you need to understand is that while capacitors cannot change voltage instantaneously, inductors cannot change current instantaneously. And this is the most important thing in getting your initial conditions right, is knowing what happens with the inductors and the capacitors at time t equals 0, because that's going to be, the most primary. I mean, the current that the inductor has before t equals 0, right before t equals 0, has to be what it has right after, and you can count on that more than anything else. So let's take a look at an example of a circuit with an inductor. Let's say we had, let's give it a current source and a switch and an inductor. I have a resistor there, and over here I have a resistor. And let's say that this resistor is 10 ohms and this resistor is 5 ohms, and this is a 2 amp current source. And I'm going to say that at time at t equals 0, the switch had been closed for a long time. Those are the sort of thing that you want to be paying attention to. When you see words like "for a long time," that means that whatever it is that you're looking at has had enough time to reach a steady state condition. What are IC of 0 minus, IC of 0 plus, IC of 0, VC of 0 minus, VC of 0 plus, VC of 0, and let's also find IC at infinity and VC at infinity. So let's find all of those things. And let's say this is 0.1 Henry. All right, so the switch had been closed for a long time, and then we're going to say it opens at t equals 0. So the first thing you always need to do is look at 0 minus. So what did the circuit look like right before you opened the switch? Well, it had been closed for a long time, so that means that the inductor has had time to reach steady state, which means it will act as a short circuit. So that's what's happening. So this is t equals 0 minus, which also means that if the inductor is acting as a short circuit, that no current is flowing through this side. So there's no current there because of the short circuit. So when you have a short circuit, the current will always choose to go through the short circuit rather than through some resistor that it's in parallel with. because why would it go through a resistor when it has a short circuit with no resistance at all to go through instead? So here's our inductor, but it's acting just as a straight wire. So because of that, all we have here is we have current, and that's all it's doing, is it's just going around like that. And so everything is in series. Things in series have to have the same current. So at 0 minus, at t equals 0 minus, our current, so IC of 0 minus, has to be 2 amps. Now, there is no voltage difference across a short wire, a straight wire. It's the voltage difference across it is going to be 0 because it's a conductor. So VC of 0 minus equals 0. So that's at 0 minus. Now, we know that the current cannot change, and it's in this direction, so it's going down. That's the direction that it is. It cannot change instantaneously, so IC of 0 also has to be 2 amps. Okay, so now let's look at 0 plus. Let's see. So I don't know how to use my new screen recording software, so I stopped the recording by accident. So eventually I'll have to combine these two videos, so we got a new video. So now we're looking at 0 plus. So at 0 plus, the switch is now opened. And so with the switch open, that means that the current source is no longer providing any current to the inductor. And we know that the current through the inductor has to be 2 amps. Now what's going to be different, so this is IC of 0 plus. What's going to be different is VC, not C, IL. And did I do that on the first? I did C instead of L on the first video. I'm so used to saying VC and IC. So this is L. L for inductor. I don't know why L is for inductor. But anyway. So the voltage can change instantaneously, and in fact it does. And so the voltage of this inductor has to be equal to anything that it is in parallel with. And it is in parallel with this resistor over here, which is, what did we say it was? 10 ohms. So it has to have the same voltage across it as the resistor does. Now the current is traveling up through the resistor. That means this side is the positive side and this side is the negative side. Because the side where the current goes into a resistor has to be of higher voltage than the side where it goes out. Because a resistor always dissipates energy. And so if you're losing energy, you're losing voltage, it's going to be smaller on the other side. And so that means our inductor also has a voltage with that polarity. Now, what is its voltage? It's going to be the same as anything it's in parallel with, because things in parallel have the same voltage. How can I get the voltage across the 10 ohm resistor? You can just use Ohm's law. V equals IR, and V equals 2 amps times 10 ohms, or V equals 20 volts. And so the voltage across the inductor at time t equals 0 plus is 20 volts but it depends on how it's labeled in the problem. So if it's not labeled, then you might want to like draw how it's labeled, because it's 20 volts if it's labeled like that. If it was labeled with the other polarity, if it was labeled like this, then you would say that it's minus 20 volts. Okay, so we know IL of 0 minus equals IL of 0 equals 2 amps. And VL of 0 minus equaled 0 volts. And VL of 0 plus equals 20 volts. Now that's going to quickly go down, because what's going to happen is, now that this is not connected to any power source, the inductor acts like a current source, but its current is getting smaller and smaller with each passing time, because it does not have anything else in the circuit to provide any more energy. So it's just going to dissipate all of its energy. So now we can look at VL at infinity and IL at infinity. So at infinity, once again, it will have come to a steady state, so we could draw it as a straight wire, but it's a straight wire really with nothing in it, because it has dissipated all of its energy. So at infinity, then we'll have that IL of infinity is 0. So that was what I wanted to show you.